Thanks very much. I'm Dave Blei from Columbia, and I'm going to talk about inferring stardust with variational inference. Um, Thanks very much for inviting me. I have two remotes. This one is not the one to use. So I wanted to start just by, before getting into stardust, talking a little bit about the type of machine learning that we work on in my group. So it goes without saying these days that we have complicated data in almost any domain you can think of, including physics, of course, and we want to make sense of that data. So what does that mean? Well, what complicated data means is many things. Initially, we might think it means we have big data sets. We have massive collections of data like we might get from a big telescope. But it also means other things too, like our data could have elaborate structures and relationships encoded in it. It's not easily encoded as a matrix. Or it could be different interconnected modalities, different types of measurements that we're trying to simultaneously analyze. These are all ways that data can be complicated. What does making sense of data mean? Well, again, there are many ways to think about making sense of data. And here I want to differentiate between these three tiers. So initially, in most machine learning work, making sense of data means we want to make predictions about the future. We're going to ingest a big data set. We're going to tacitly assume that our next data comes from the same process that that data came from, and we're going to try to predict what's in that next data. Right? That's what neural nets and linear regression, things like that do. We might want to do more. We might want to identify interpretable patterns. We want to ingest the data set, fit a machine learning method to that data set, and then somehow investigate the result of that fitting procedure to understand something about the data, to learn something that helps us explain it. And kind of most ambitiously, we might want to do science, confirm, elaborate, and form causal mechanistic theories about how the world works based on the data. This is, in some sense, the grail of statistics and machine learning to understand the way the world works by looking at the data that we observe about the world. So the field in machine learning that I work in is called probabilistic machine learning. It's also called applied Bayesian statistics. And it's about developing machine learning methods that connect our domain knowledge to the data we want to analyze. And the idea is that probabilistic machine learning gives us a way to articulate our assumptions about the world, articulate what we know about the world, and then compute under those assumptions about the data set that we observe. And our goal in this field, the goal of me and many other researchers, is to make this kind of research expressive, meaning I can articulate many types of assumptions with it, scalable, meaning I can analyze massive data sets with it, and easy to develop, meaning it's easy to develop. Good, so just some examples. These aren't about physics, of some things we've done in my group with probabilistic machine learning. This is a way to, we work a lot on the identifying interpretable patterns aspect of the problem. These are discovering communities in big networks. This is doing neuroscience, analyzing fMRI data and which parts of the brain are active when under different kinds of stimuli. This is a topic model. This is looking at patterns of words that are used, that are associated under a single theme, discovered by looking at electronic text data. This is an analysis of genetics, of finding ancestral populations that mix to form observed genotypes. This is some recent work with an economist on looking at patterns of consumer behavior. I know this workshop is about physics, but this is an important econometric result that crackers and cheese go together. That's what this shows you. So this is the kind of work we do. We work with domain scientists. We get some data from them. We talk to them about what they want to assume about their data, and we find interpretable patterns by analyzing it. And all of those projects kind of go through what I like to call the probabilistic pipeline, which I've illustrated here. And the idea is that we start with our knowledge of the world and a question we want to ask about it. We use it to make assumptions. Our assumptions are articulated in a formal statistical model that involves hidden variables. Those are unshaded nodes. And observed variables. Those are shaded nodes. Then we take our data and our model and square them together. We infer what these hidden nodes are given these observations. We're going to do that with stardust in a second. Okay, so that's this inference section. Discover the patterns in the data. Can you hear me if I'm away from the mic? And then finally, we use, of course, those discovered patterns to do something, to form predictions, to explore, to interpret, to do causal inference, whatever it is we want to do. And so I like this picture because separates these key activities of articulating our assumptions, computing about those assumptions, and then doing something with the results of those computations. And this makes it easy to collaborate with domain experts on solving statistics and machine learning problems. Okay, so that's the general area of machine learning that we work on in my group. So I want to talk in a little bit more detail about our work on stardust. So this is work that's in progress. We've been working on it for like four or 5 months with Andy Miller, Lauren Anderson, who are both here, and Boris and David. And so this is some work we've been doing at the Flatiron Institute. And the idea is, and I will just, the caveat is, everything I know about stardust, I'm going to say in the next 10 seconds. Okay? We measure stuff in the universe, and our measurements are mediated through stardust. So when we go and make a measurement of something way out there, also Lauren is here. She can correct me if I say something incorrect. So we make a measurement, and our measurement is not just simply a raw measurement of the point that I measured, but rather it is going to be affected by all the stuff in between me and that point, the stardust. And what we want to do is take a big set of measurements from the universe and infer the map of stardust at each location. How much dust is there at that location? Lauren? Okay, thumbs up. So that's the plan. And so this is a picture of real stardust. This is the picture I drew about this problem, okay? So the idea is, so I want to articulate for you what the hidden and observed elements are in this problem. Okay, so first the location, xi, is in 3D, and Earth is at x naught. Okay, so you can see there, I'm going to use the pointer. So here's Earth, this is obviously Earth, and this is x naught, okay? And what's going to happen is we're going to make an observation. Here's xi, we're going to make an observation at xi, and what we see is ai, which is kind of a noisy realization of whatever it is we're measuring at xi, but taken through the map of dust between us and xi, okay? And so rho of x is going to denote the dust map. Rho of x is how much dust there is at any location x. And the attenuation is this integral between Earth and wherever we're measuring of rho of x. And the measurement that we actually receive, ai, that's going to be some noisy realization of that attenuated measurement. Make sense? Okay, so just to be clear, what's observed and what's hidden here? Well, we are assuming for now that we observe xi. We know the location that we're measuring. We, of course, observe x naught. We don't know rho of x. That's what we're trying to figure out. We also don't know e of xi because our measurement has some measurement noise associated with it. Clear? Okay, so what we observe is a and x, and everything else is latent or hidden. Okay, so as promised, we're going to take those assumptions, turn them into a probabilistic model. And one way to articulate a probabilistic model to understand its assumptions is to describe its generative process, okay, the imaginary process by which it creates its data. And here that generative process is pretty simple, but it works as follows. First, we're going to generate a dust map, rho of x, from a Gaussian process prior. Okay, Gaussian process prior is simply a distribution over functions where the evaluation of that function at different points is the covariance between the evaluation of that function at different points is defined by what's called the kernel function, or the covariance function. And so rho of x comes from a Gaussian process, which is mean zero and has a covariance function k. Okay? I'll explain k in a second. And then once I have that dust map, so I choose the dust map randomly. It gives me a map of the dust of the universe. For each observation, then, I draw whatever it is I got to see from a normal distribution whose mean of xi, that's that integral I showed you before, here, that integrates the latent dust map, and some measurement noise. Okay? That's the generative process. We're going to use the squared exponential kernel covariance function that looks like this, where L essentially controls the a priori smoothness of this function that we are assuming we're going to see. Clear? The prior hopefully doesn't matter as as much as the posterior. So our data then are noisy observations where I see my observation AI at different locations xi. That's a big collection of observations from the universe. And I want to ask the question, what is the latent dust map that best explains the observations I saw? Okay, and in probabilistic machine learning or applied Bayesian statistics, we do that through the posterior. Everything is situated in a joint probability distribution. So the conditional distribution under that generative process of rho, given the data, provides for me the dust map that best explains my data. Make sense? Okay, so that's our problem. We're going to estimate the dust map with its posterior expectation. Given a bunch of measurements, we're going to estimate rho with the posterior expectation, what rho best explains those observations, and then we're going to use that as our dust map. Okay, and so in the second part of this talk, I'll tell you at a high level how we solve this problem. This problem is hard to solve. But first, let me show you some results. So just imagine that we can posit this model, we did, and that we have some mechanism to take our data and infer the conditional distribution of this function given the data. Okay. So as a sanity check, we generated data from a 2D dust map. Here's a 2D dust map. Here's some noisy observations from that 2D dust map. These are just scalars, but of course at locations. And then here's the inferred dust map. Okay, and so you can see the inferred dust map sort of looks like the true dust map. That's a sanity check that the inference procedure is working well. Now, to do something slightly more than a sanity check, we simulated the universe with a non-case simulator. I learned the word yesterday, but I knew that we were simulating the universe. Where this is a realistic simulation of these kinds of measurements. And here is the of EI at different locations. This is a 2D slice. We're, of course, generating a 3D universe here. And so this is a 2D slice of the universe. These are the true EIs. And then here is the inferred dust map in that same 2D slice. Okay, so just to be clear, this simulates the situation where we generate a real universe. We get noisy observations from that real universe, which has a realistic dust map. And we are able to recover that dust map from that simulated universe. Plot tells us that it works. It also tells us a little bit more that assumed prior smoothness, L, makes a difference in how well we can recover the dust map. And so we need to fit that with a empirical Bayes procedure. Yeah.
You might have clouds and patches, but you
so why use the posterior expectation?
as opposed to
We could draw from it. I mean, hopefully
it does have this effect of smoothing, of removing.
Absolutely.
Just because you don't know where it is doesn't mean you don't know.
Yeah, that's true. So, right. So ideally, we have enough data that this is peaky and that posterior, and that the posterior variance is small, and draws from this are going to look similar. But you're right. If not, then taking multiple draws of this and then calculating some function is going to help us take into account that posterior. Okay, good. So what's next for this work in progress? Well, our main goal is to scale up to the Gaia data set. Okay, so we want to scale up this approximate posterior inference algorithm with this complicated Gaussian process model to 1.3 billion measurements. That's one of our next steps. Another next step is to consider the selection mechanism when, where we point the telescope. Is it even a telescope, Lauren? Satellite. Where we make our measurements is not necessarily random. And does that affect our inferences of the dust map? This is something to think about, and Bayesian statistics provide some interesting methodologies for accounting for the selection mechanism when making inferences about some unknown variable. And a final next step is to jointly model the noisy measurements and location. So that model's here. So the simple model, of course, had X pointing to the observation. These two were observed and both came from rho, from the dust map. But here, we're going to more realistically model this situation that we're in, which is that we have a noisy estimate of the inverse distance between where we are and here is the true distance, x, and we want to understand that we have a noisy measurement of x. We have noisy measurements of color and brightness. Here is the true color and brightness at the true location. And for those of you that know graphical models, you can see that when we acknowledge this situation, the noisy measurements and the noisy locations that we are working with, everything, and acknowledge the hidden dust map, everything becomes dependent, right? In you stare at this graphical model, you can see that my measurement, the true color and brightness at location 1 is going to be dependent on the true color and brightness at location 5 and at location 9, etc. Everything becomes dependent. So when we fit the model in this way, we'll be able to refine our estimates of various locations and stars based on the other locations and stars. Okay, and this is one of the advantages of these graphical models, is that they let us, particularly when we have latent variables that live outside of the data plate, they let everything become dependent and let the data speak to each other to help refine our estimates of the things we don't know. Okay. So that's everything I was going to say about stardust. But of course, all of that required that we magically can calculate the posterior distribution, the distribution of rho, given the data. And because this is a workshop about physics and machine learning, I wanted to tell you a little bit about how we do that, because it involves, from the 1990s, taking an idea from physics and importing it into machine learning. So just to remind you of the big picture, here's this probabilistic pipeline. Posterior inference is the key algorithmic problem, right? So I have my model, dust map, and stuff like that. I have my data, Gaia data set, and I want to infer the dust map from the Gaia data set, right? This is where we have to do some work. How do we calculate P of rho? And in general, posterior inference answers the question, what does this model say about my data? And our goal, in general, in probabilistic modeling, is to make posterior inference general and scalable. General meaning no matter what kind of crazy dust map distribution I write down, I can calculate the posterior. Maybe I want to refine that prior. Maybe I want to use something else. And scalable means that even with the Gaia data set, I can calculate the posterior part. So more formally, in probabilistic machine learning, we set up a model. It's a joint distribution of hidden variables z and observed variables x, p of z and x. In this case, z is the dust map, and maybe the noisy locations and stuff like that. X are the observed variables. And then when you set things up this way, inference about the unknowns is through the posterior, the conditional distribution. Probability you learn. But the problem with this, when you're working with things like the Gaia data set, is that you can't calculate the denominator P of x. Actually, even a small data set, you can't do that with the model because the model is so complicated. Okay? And so for most interesting models, that denominator is not tractable, and we need to approximate P of z given x. Algorithmic question in probabilistic machine learning. How do you approximate P of z given x? So we use something called variational inference. And the idea behind variational inference, if you print a bunch of papers about it, it looks really complicated. But the idea is really quite simple. And this picture tells you, and in my opinion, everything you really need to know to understand what variational inference is. The idea is this. Variational inference solves this inference problem, approximating P of z given x with an optimization problem. Okay, if you're familiar with something like MCMC, this is different from MCMC, which defines a Markov chain whose stationary distribution is P of z given x, and then you sample from it forever until you get a sample from this. Here we're going to use optimization to solve the same problem. The idea is as follows. I'm going to use this pointer again. So imagine the space on the slide here. Every point is a distribution over z, a distribution over the latent variables. So this point is the posterior, P of z given x. That's what we care about. That's our target. The idea in variational inference is to first posit a family of distributions, Q of Z that lives in that space. Okay, so this is a family of, I feel like I shouldn't do that. The family of distributions here. All right, every point in here is another distribution of Z, and it's parameterized by nu. So every point in here is it's indexed by nu. Every point in here is a different setting of nu, which are called the variational parameters. And what we do is we start with some initial variational parameters, nu and it, and then we optimize. We march through and search through this space of nu until we find nu star, which is closest in KL divergence to the exact posterior. Okay? So this turns the inference problem, the approximate inference problem, into an optimization problem. As you can guess, the family is selected to make this optimization tractable, and as you might also guess, selecting the family in that way means that the space of Q does not contain P of Z given X. If it did, we wouldn't have a problem to begin with. Okay, that's variational inference, and you know, there's a stack of papers a mile high about variational inference. They're all working on some aspect of this problem. Okay, and KL divergence. This is just in case you're not familiar, this is a way of measuring a distance, not a proper distance, but a distance between distributions. Optimal variational distribution, back posterior that we care about. Okay, so here, this is a simple example. Here's a mixture of Gaussians. This is variational inference to do inference on a mixture of Gaussians. A Bayesian mixture of Gaussians is an example of a non-tractable model. And here we start with a bunch of data, and what we're plotting here are the contours of the posterior predictive distribution of the next data point. Okay, and so the point here is that you can see that as this optimization proceeds, we get closer and closer to a good approximate posterior. I'll talk about this objective function in a second. This is the objective function, the KL divergence, that gets closer and closer to the exact posterior as we march through in this optimization. Okay, so in just a touch more detail about variational inference, the KL divergence, the thing we're trying to optimize, the measure of closeness between distributions that we're trying to optimize, is intractable. And so what BI optimizes is something called the evidence lower bound. Okay, this is which is a lower bound on the log probability of X that is equal to the negative KL divergence up to an additive constant. Put simply, if you optimize the evidence lower bound, you're also optimizing the KL divergence, even though you can't calculate the KL divergence. Okay? This is the evidence lower bound. It's going to be a function of the variational parameters, and it has two terms. The second term is the entropy of the variational distribution. The first term is the expectation of the log joint. All right, and so intuitively, we're setting the parameters nu. When we set the parameters with respect to the first term, we're trying to find Q's that place mass on configurations of latent variables that explain the data. That's what expectation Q log P of X comma Z does. Okay, so that's trying to say, I want my Q to put its mass on latent variable Z that really explain well the data that I saw. The second term says, I also want Q to be diffuse. I don't want it to just be a point mass at those. I want it to somehow be diffuse. And what variational inference optimizes. This is the same as optimizing that KL divergence. Okay. So what are the challenges to doing this? There are several. There are many. First, when we have complicated models like a Bayesian nonparametric Gaussian process dust map model that I showed you, calculating these expectations is hard. Okay? We can't even calculate these expectations. Okay, so that's one. Two, when we have massive data sets, like we do with this Bayesian nonparametric Gaussian process dust map model I told you about, then calculating the gradient of this objective function is also hard because I have 1.3 billion measurements, and I want to calculate the gradient of this objective function that involves all of them. Three, this is not convex. Okay, so these are all difficulties in doing variational inference. Happily, this is the real story of machine learning, in my opinion. Stochastic optimization, which is like a 70-year-old algorithm from Robbins and Monroe, has helped us alleviate these challenges in variational inference. So in particular, and this slide is part of a 6-hour tutorial I have about variational inference, so I got 10 seconds left according to that clock. So I won't go into details about this, but you can ask me later, and I'm happy tell you about them. So there are two ideas, black box variational inference and stochastic variational inference. They both use stochastic optimization to help overcome these challenges. Black box variational inference, what it does is it figures out how to write, it doesn't figure out, researchers figured out how to write the gradient of this objective function as an expectation, and then sample from Q to take Monte Carlo approximations of that expectation. That gives us noisy gradients that we can use inside a stochastic optimization algorithm. That helps alleviate these intractable expectations. Idea two also creates a noisy gradient of the elbow, and it does it by taking mini batches of data, like one does in deep learning, for example. Ideas together help make applied Bayesian statistics scalable and helps us handle intractable likelihood functions. Okay, and this is how we got these pictures, right? We need to use all of these tricks to get these pictures with the stardust. But by the way, this is also how we get all of these pictures too. So, you know, the variational inference we use as a general purpose tool to do posterior inference. Okay, so I know I'm out of time, but I'm going to continue just for a few more minutes. Because there's time for questions, so I'm just eating that time. Because this is a workshop about machine learning and physics, I wanted to just give you one slide about the history of variational inference because it involves physics, so I feel like you should pat yourselves on the back for this. So where did variational inference come from? First, it's adapting ideas from statistical physics to probabilistic inference. And from my emailing around the different pioneers of variational inference, it started with this paper by Peterson and Anderson from 1987, who used mean field methods to fit a neural network. Okay, so from my understanding of the history, this paper came out in 1987. Then Lawrence Saul, who's a physicist, who went to study machine learning with Mike Jordan as a postdoc at MIT, in the 1990s, brought this paper to their group. They read it, and then they started generalizing the idea to many probabilistic models in the 1990s. Parallel, in the kind of neural net world, Jeff Hinton and others developed mean field methods for neural networks again, and then Radford Neal and Jeff Hinton connected variational inference to EM, which led to more variational inference for probabilistic models. But the point of this is that this began adapting an idea from statistical physics to a machine learning model. Now, I mentioned that today we can do more with VI than we could in the 90s. So there's lots of new work to make it scalable, drive faster, and more accurate. And it touches on lots of areas in machine learning. And the punchline is VI is a tool that we can use for many more things than we could in the 90s. Okay, so that's my talk. Probabilistic ML helps connect domain knowledge to data. VI is powerful, and we use it to do stuff with space. I also want to mention the work by Jeff Ray here and Andy and others on Celeste, which is another great example of doing scalable astrophysics with VI. Oh, I see. So I was asked to have open questions at the end, so here are just a couple, and then I will end. One, VI stems from old physics ideas. Are there new physics ideas that can help? It's like, I don't know what year it is, but it's way past 1987. Two, I won't go into it because David is standing up, but this cartoon identifies, in addition to how to understand VI, all the challenges we have for VI. Thinking about each scratch on this cartoon can identify a place where we can improve VI, the optimization method, the class of distributions, and so on. And one I want to bring up for physicists is this. So here we assume, usually, that we can calculate the likelihood, but you build these big, complicated simulators in Fortran that we can't calculate the likelihood, but we can sample from. How do you do variational inference in implicit models? This is a great new area that some and finally, how do we use neural networks in graphical models? I'm done. Thank you.
Excellent. So a few minutes for questions.
What's the extinction and distance data that you're using
What's the what?
for the estimation of the dust distribution?
Yeah.
You're using extinction and distance data. Where's that from?
Well, it came from the simulator, but I will defer to Lauren, who can understand both the question and give an answer.
For the real data, we're using
Okay.
So this may be more a question for you. you kept showing the Planck map. You're not using as a prior, the Planck dust data. That gets to the question about when you draw from. We have a lot of other information that you could draw from, right? One is that, and the other, and I guess it's a question about the form of the kernel. You chose a particular form of the kernel, but we actually know what the correlation function is of the dust, and we know that it's clumpy, and we have all this information on the dust properties that we have more knowledge.
Right. Yeah. So
I guess it's both a question for Lauren, why not? Why didn't you include it on the astronomical side? And for you, is it does it make the problem more intractable if the kernel had more structure?
Right. So I'll answer briefly, and then we'll turn it over to Lauren. But the game here, it's kind of a dance where simple priors make computation easier. And often the data is rich enough to let the simple prior, as long as it's diffuse enough, show us the map, literally. But I like to think of this pipeline really as this loop here in the slide I skipped, where at the end of the day, we're not done, right? We picked a prior, Gaussian process. It's pretty complicated, but it's a prior on functions. But of course, we could make the prior better. Would it make a difference? Well, Bin, you mentioned sensitivity analysis in her talk, in her excellent talk yesterday, and that's where sensitivity analysis comes in. Once we do whatever it is we're going to do, we want to then figure out where it went right and wrong. And it might be that taking more knowledge from astrophysics is the answer to making that prior better. It might also not be. It might be that that induces too much computational overhead to make it useful.
Like
exactly, that's what I mean. With a diffuse enough prior, it might be that
it's not even
different. Tells us we would learn that knowledge. But of course, it's again this dance. Like it might be more efficient to bake that knowledge in order to find.
What only if it's not independent?
It might be that knowledge is the same as the data.
Computed from measurements that were quite similar.
It still makes inference.
I don't know. I'm just
because it
speculating.
nudges the inference in the right.
Yeah, the question's about
It's actually related in an interesting way. Dust in absorption of light. Dust then absorbs the light and re-emits it. And we have data absorption and it's the same. We have this other set of data in a way that dust properties perfectly, we would know how they're related. Probably just related by a relatively smooth function. So it's an interesting case where the data isn't redundant, but there is a deep physical connection.
But I mean, I agree that when you work on the prior, which is important to do, then you make this more complicated, P of z given x. But of course, this is part of the plan here, is to build this iterative cycle of better dust models. I now know I'm never going to give this talk unless Lauren is there.
So actually, at the same talk about the prior on the kernel.
Yes.
Right, that eventually will diffuse. But the other side is that if you already put into some physics, you get more precise answers.
Yeah.
Right. So in that sense, you probably want to do the
That's right. No,
modeling of the clumping.
I think working on the prior is a good idea, and also the L, the smoothness of the prior smoothness makes a difference, and this is why we do empirical Bayes. So we fit L with empirical Bayes, and that's important here.
Question. Since we heard variational inference and approximate message passing yesterday, they always look like very similar to me. If anybody could comment on what's different or what's similar there.
Well, both fit into this picture. So often things like BP and EP and they correspond to metrics here, other than the KL, but they still can be thought of as optimization procedures that search the space of a family of distributions to find a target distribution that's close to the conditional distribution that you care about. And you have to squint to sort of see it, but that's the idea. That's right. Good point. So again, this is another dance that we have to do. So often we pick. So this optimization procedure is the computation that you have to do. And how easy that optimization is or how hard it is depends on the family queue. If you pick a very structured queue and a big class of families, it's expressive, but it might be harder to optimize. One of the interesting open problems in variational inference is a formal way to think about the trade-offs between the size of the family of Q and the complexity and possibility of the optimization. It also interacts, this is more bad news, with the non-convexity of the objective function. The objective function depends on the family Q, and so a very expressive Q might have more local minima. You might be more subject to falling into them. There's some really interesting work. Max Welling has done some really interesting work on what's called amortized inference, where Q itself depends on the input data. There's work on structured variational inference, which adds, so I never said what mean field is. Mean field means we assume each latent variable is independent but governed by its own distribution. This seems inflexible at first, but it's pretty flexible because you can capture any posterior marginal of any of the latent variables. That said, adding structure can help, especially if you care about posterior correlations. Expands Q, makes optimization harder, but there's a series of works on this. Yeah.
Inference seems to be an old idea, and I don't see it applied very often in cosmology and astrophysics. Do you know why are the reasons?
Well, again, so there's this paper called Celeste, which is really nice work. That's one reason. I think the main reason is that we didn't have this picture, so no one knew how simple it was.
Okay. And my question is also about this. How do you foresee that we could include neural networks into this?
Yeah, that's a great question. So there's again, Max Welling is an expert in this. There's a line of work a new line of work in machine learning, probabilistic machine learning, on what are called deep generative models. And what that means is, so we've been trafficking in graphical models like this for a lot of years, where I'm just using this as an example of a graphical model, where one has to specify, what is the form of the distribution of. You might decide it's gamma or Poisson or Gaussian or Bernoulli or whatever it is. You have to figure out that functional form, even if there are unknowns, right? Now, in generative models, what we do is the form of that density depend on the output of a neural network whose input is xi. Okay? It takes a second to describe, but unfortunately, statistically, it's complicated, and inference is complicated too. And I think still working out the details. Like just applying BI naively to those models doesn't always work the way you would hope it does. But there's a lot of progress on that, and it's an active. I think it's very interesting future direction. I'll learn the inverse CDF. Yes.
The gradient.
Not defined, right? It's derivative that's defined. Gradient needs you to choose near the birth structure. The one that came out of the box, or?
Right. So let's go to this picture where. So here I'm telling you that we're going to do some kind of to some parameters to a probability distribution. Gradient. So there's a lot of work in variational inference on using natural. That's the key to scaling it up. Some models, some models it makes sense both sometimes that's too expensive, and then settings I'd be interested in learning